Thank you all for joining us today. It is wonderful to see a nice large audience and be back in person. I know that we ended up delaying this lecture for a number of months, if not years, because of COVID, so it's wonderful to be back here with everyone. I will say officially welcome to the 2022 Steve and Sylvia Burges Endowed Lectureship. This lecture provides us an opportunity to hear from members of our community, from the Distinguished Civil and Environmental Engineering faculty, and learn how these men and women have found their way in civil engineering and come to accomplish great deeds, and probably no more accomplished than Steve Kramer, who is giving our lecture this afternoon. Many thanks to Steve and Sylvia, who make the lecture possible and are going to ask lots of good questions as the lecture comes to a close, I'm sure. This afternoon, we have the opportunity to learn from one of the world's foremost geotechnical engineers, and I don't say that lightly. UW-CE Professor Emeritus Steve Kramer has done amazing things during his career. I had the opportunity to read through his CV and am incredibly humbled by all that Steve has accomplished during his career. He's made numerous significant contributions to advanced geotechnical engineering research and practice in the areas of soil liquefaction, site response analysis, seismic slope stability, and hazard analysis. And through his research engagement and collaboration with the professional engineering community and through his textbook, he's had a real significant impact on the practice of geotechnical engineering and geotechnical earthquake engineering. Something that we all strive for, but certainly Steve has accomplished much in that area. Throughout his career, the importance and impact of his work has been recognized by the community, both the academic community and the practicing community. He's been the recipient of, if not all, then almost all of the major ASCE awards for which he was eligible, including the Casa Grande Professional Development Award, the Huber Research Prize, the Norman Medal for Most Impactful Paper twice. Additionally, he won the Nigel Priestley International Prize for Earthquake Engineering and the Nabor Carrillo Lecture Award from the Mexican Society of Geotechnical Engineering. Most recently, he's been elected to the Washington State Academy of Science and has been named a UC Berkeley Distinguished Alumnus, as well as elevated to Distinguished Member of ASCE. And 2 years ago, just as COVID was getting started, he was elected to the National Academy of Engineering, the epitome of success as an engineer. And thus, not only does this lecture provide us an opportunity for learning a little bit about Steve's career and life and a lot about geotechnical engineering, or maybe he will flip it, but it's also just a wonderful opportunity to recognize and congratulate his accomplishments. With that, I will say welcome, Steve, and we look forward to hearing about your accomplishments, personal and professional.
Well, thank you, Laura, and thank you all for attending on a Friday afternoon. I'd like to thank the Burgesses for their generous donations to the department and support of the department, and for their generosity in supporting young faculty. I can recall when Diane and I were invited to their house shortly after we joined the university, came here in 1984. It meant a lot to us, and Steve's generosity as a colleague has also been important and very much appreciated by me. So in preparing this lecture, I looked at the previous Burgess lecturers, and there were kind of a variety of styles that they went through their lectures with, and I thought that I would do something maybe a little bit different and talk about some of the things that I've been involved with, projects I've been involved with. And I tried to pick 4 out, all in the area of geohazards, which is where I've spent a lot of my professional career dealing with. Geohazards can be described as adverse geologic conditions that can cause lots of damage, can lead to loss of life, loss of property, and tremendous levels of damage. They can be of natural origin, or they can be caused by human activities. They can cause deaths and injuries. They can cause economic losses. They can be localized to a particular structure or site, or they can extend over very large areas and have great effects. Some occur very frequently, some occur only rarely, some occur very quickly and dramatically, and others much more slowly. They can interact with each other and cause additional damage, and they can be very easy to ignore, and they often are ignored, at least until they occur. So some of the examples include landslides, like the Oso slide that occurred in this area a number of years ago, but also flow slides, debris flows, and rockfalls, all capable of causing tremendous amounts of damage. Earthquakes are important geohazards. They can cause soil liquefaction. Fault rupture can damage structures like this dam in Taiwan. Soils can amplify ground motions very strongly, and in some cases, stronger than the structure was anticipating, and lead to structural problems. And they can cause failure of lifelines, like buried gas pipelines. Volcanoes certainly are geohazards, not just due to lava, as in Hawaii, but due to lahars, large landslides that come off the flanks of volcanoes, and they're hazards often for mountain rainier. Expansive soils are soils that are very sensitive to water. They swell when their water is introduced to them. They shrink when the water goes away, and that causes the ground surface to raise and lower seasonally during wet and dry seasons. That causes a lot of damage, particularly to brittle structures, lightweight structures. It causes a tremendous amount of damage to pavements. This hazard doesn't get a lot of publicity, but it causes about $13 billion in damage a year in the United States. Sinkholes are a big problem in certain areas like Florida, where they have a lot of limestone, and the limestone will dissolve in water, so flowing groundwater produces caverns that, if they become large enough, have a roof that collapses. Settlement and subsidence can occur when groundwater is withdrawn for, say, for irrigation purposes, as in the Central Valley of California. You have tremendous amounts of subsidence, 30 feet or so in that area, and that's had an effect on the design and operation of the California aqueduct that supplies drinking water to 29 million people. It also has an effect in the southern part of the San Francisco Bay, in the Silicon Valley area, where over 10 feet of subsidence has occurred due to drinking water withdrawal. Permafrost is an important geohazard in northern climates. The freezing ground draws water up towards it, and the ground level lifts. And then when the permafrost thaws, big problems for pavements, problems for buildings can occur, infrastructure, and can even trigger slides in some cases. Now we're more concerned about permafrost due to the knowledge of how much carbon dioxide is released when permafrost thaws. And so that tends to warm the atmosphere, which causes more thawing of permafrost, which leads to more carbon dioxide. So that's a big environmental problem. Soils can be moved, soil particles can be moved by flowing water. And erosion, scour, and piping are important hazards. If we put a bridge pier down in a river, the water speeds up to get around the bridge pier, and it starts removing soil particles from around that foundation. And they can undermine the foundation and lead to collapse of bridges, or exposure of the foundations to the atmosphere, and leave them more vulnerable to subsequent flooding events. Internal erosion can occur. In Teton Dam in 1976, a little wet spot appeared on the downstream embankment, and that turned into a trickle of water moving down, and within a few hours, that trickle became a stream, and not long after that, the entire dam was breached, and it failed. The entire contents of the reservoir were released, caused downstream flooding, killed 11 people. Induced seismicity is a relatively new, we think of it as a new geohazard in a lot of cases, but if we go back to the construction of Hoover Dam in an area where earthquakes did not occur, as the reservoir was filled and reached about 60 or 70% or so of its eventual height, earthquakes started occurring in an area that hadn't had them before, partially probably due to the weight of the reservoir and partially due to water that's seeping in and kind of lubricating the faults. That happened at Koyna Dam in India when it was filled, and Oroville Dam in California. Now we see induced seismicity in the news more because of fracking occurring. And in fracking, large quantities of water are injected back down into the ground, and that tends to reduce the strength of faults and lead to earthquakes occurring. We also see induced seismicity in areas where gas is being withdrawn. and that causes new faulting to occur. This is a big problem in the Netherlands, of all places, where they never have earthquakes, and nothing is designed for earthquakes, but they're getting small earthquakes now, and there's concern about structures and the levees that protect the country. Mining activities have for a long time had geohazards. Large landslides have occurred in open pit mines, and we've all known about the hazards of underground mining activities. Tunnels, even lined tunnels, can collapse and cause damage and potentially loss of life as well. So these are all important geohazards. In my talk, the title is Big, Small, Fast, and Slow. I'm going to reverse the order a little bit and talk about the small first. It's not as good as the others, so we're going to start off with that. And it has to do with the first project I worked on. After I got my master's degree at Berkeley, I went to work for a kind of small to medium-sized consulting firm rather than the big firms that most of my classmates were signing up with. And I wanted to get a lot of exposure and responsibility in an early stage and kind of learn what the geotechnical engineering business was all about. And so after I'd been there about a week, my boss came in and said, "I need you to design an earth dam." And I thought, well, this is great. I mean, that's like the big leagues of geotechnical practice, so I'm going to start off designing an earth dam. So I started thinking about the kind of earth dams that I'd studied in my classes, and I realized I was not going to be designing an earth dam like this, but I thought even a small earth dam would be kind of cool to work on. So any one of these I would have been happy to work on. Earth dams can be complicated. They're put in complicated areas geologically, at least often, but they have things like clay cores for impermeability and shells that hold them up, and drains and filters and all kinds of things. All the bells and whistles are kind of indicated here. And I knew that my dam was not going to, I called it Kramer Dam. It was not going to have all of the bells and whistles, but it would have some at least. It was going to have an 8-foot wide crest, 3-to-1 upstream slope, 2-to-1 downstream slope, and it was going to be almost 900 feet long. So pretty cool. But this drawing turned out not to be to scale, and it's really not to scale because I was then told that my dam was going to be 8 inches tall. So if I drew it to scale, it would look more like this. And my Kramer Dam turned out to be needed because a water tank was going to be constructed on a level plot of ground near a park. And water tanks can leak, and the owner of the tank was required to contain the water in case the tank failed. And so my dam, Kramer Dam, provided that containment. I'm happy to say it was successfully constructed in 1982. Don't have any photographs, but it marked an illustrious start to my career as a geotechnical engineer. So we'll go move on to something a little bit bigger. I'd like to talk about some projects that I've been involved with. Don't necessarily all use or based on or use my research. Some of them did. Some of them should have maybe. It didn't, but this is one of the early ones that I got involved with, called the Storega slide, which is a very large landslide, a submarine slide that occurred off the coast of Norway about 8,000 years ago. It removed 2,500 to 3,500 cubic kilometers of sediment, generated a tsunami that struck Norway, Scotland, the Shetland Islands, and the Faroe Islands with run-ups up to 30 meters, 100 feet. The head wall is 320 kilometers long. It ran out to 400 kilometers and then continued as a turbidity current and deposited turbidites more than 900 kilometers away. It became of interest because of the 1997 discovery of the Ormen Lange gas field, which was an important gas field. It was the third largest gas discovery on the Norwegian shelf. Oil and gas are big business, and they're big business in Norway. Their country depends on that in many respects. And so it was a consortium of oil companies that did the exploration, and Norsk Hydro and Shell Norway were the leaders of it, and they were responsible for investigating the development of this gas field. It was complicated because it lies 800 to 1,200 meters below water and very close to the steep back wall of the Storega slide. However, it was very significant. The gas was going to be exported to the United Kingdom. It could have there was enough to power 22 million homes and represent 20% of the UK's gas needs. The geologic setting is dominated by flow of sediments through the Norwegian Channel to the North Sea fan. and also by multiple shelf glaciations. And so the dark dashed line here shows the edge of the continental shelf there. Glaciers came out to that point and went back several times. The Storegga Slide lies between two topographic highs, the Moray High and the Voring Plateau. So both the oil companies, the consortium, and the Norwegian government were very interested in understanding how this happened and what the implications would be for future stability if this gas field was going to be developed. There were several potential causes. They developed a group of consulting firms that would investigate these different causes. And they came up with an approach that's described in the flow slide here. There were about 5 potential causes that were initially investigated, and that was narrowed down to 3 pretty quickly. They also assembled a multidisciplinary team of experts to review these investigations and advise them as they went through their processes. And this included geologists, tsunami experts, sedimentologists, seismologists, oceanographers, and an earthquake guy, who was me. It was a very international team. There were probably 6 or 7 countries represented on this, and a really, really interesting group of people to work with. Of the causes, one was rapid sediment loading. As these sediments were being deposited, if they were deposited very quickly, they would tend to build up pore water pressures within the sediments. And it was known that a lot of landslides had occurred repeatedly coming off of the North Sea fan. They've been measured and dated back as far as 500,000 years. Numerical modeling of this whole process indicated that there would be pore pressure ratios on the order of 20 to 30% or so. So significant, but not enough to explain the triggering of that particular landslide. Gas hydrates was another possibility. I knew nothing about gas hydrates going into this process, but they could have melted as the waters warmed after the last glaciation. And gas hydrates are mixtures of methane and water that freeze effectively. And when 1 cubic meter of gas hydrates thaw, it produces 164 cubic meters of gas and a little bit of water. And so when these things thaw out underground, the pressures, the expansion pressures that are developed are tremendous. And they can cause gas to flow up towards the surface and be ejected explosively at the surface. They create large craters. They're referred to as pockmarks, and they're visible in bathymetry all around the North Sea area. But the gas hydrate zones in this particular area didn't follow the stratigraphy or the observed failure surface, except for part of that slide. They could have influenced the pore pressures, but it was not thought to be capable of having triggered that landslide. The third main cause, was earthquakes. And earthquakes in this region were caused by isostatic rebound of the Earth's crust after the weight of the glaciers went away as the glaciers receded. And from faulting in Norway, magnitude 7 or greater earthquakes were likely to have occurred in this region. It's still the most seismically active area within that region. And so the conclusion that was come to was that an earthquake was likely the trigger for the Storegga Slide that had occurred. So there were concerns on the part of the consortium and the Norwegian government about the safety of this potential development, the risk that they would be undertaking in developing it. The development was going to require templates, large steel templates that would be anchored to the seabed. Each template had 8 cells in it through which drilling would take place. The gas that was removed would have to be sent to an onshore gas processing plant in Nyhamna on the west coast of Norway through 2 30-inch pipelines. There are strong currents in this area, about 1 meter per second. And so the pipelines needed to be protected. So they'd be trenched in areas where that could be trenched with softer sediments, and they'd have to be covered by rock fill in other areas. That gas was going to go to the UK, and that was going to require construction of a 1,200-kilometer pipeline from Norway to the UK. So this was an enormous project that was going to require billions and billions of dollars to develop. So the safety considerations centered on 3 main questions. Was the area still prone to submarine slides? What could trigger those types of slides? And could the activities associated with developing this gas field in combination with natural processes trigger a new slide that would have severe consequences? So the instability threats were divided into 3 categories. One was very large Storega-like slides. Another was smaller slides that could have wiped out multiple installations, and then smaller slides that could have threatened pipelines and individual installations. And so there were the natural mechanisms that had been discussed previously, and then there were a series of mechanisms that could have been caused by the proposed construction or anticipated construction. Anchor forces, rock filling, temperature changes due to the drilling, well blowouts, subsidence due to depletion of the reservoir as the gas was removed, and then induced seismicity. And so this initiated a tremendous investigation. These are the seismic profiling lines here. They show up nicely. There were hundreds, if not thousands, of P-wave velocity profiles that were developed to essentially look under the seabed. It's kind of like an ultrasound in many respects. That was supplemented by borings that were put in under very difficult conditions. You had to go through 250 to 1,600 meters of water before you hit the seabed, and then drill 500 meters through very difficult materials in order to advance your borings. But that was done, and all of that information together provided knowledge of the bathymetry of the region, of the surface texture, and of the stratigraphy, which included both glacial and interglacial deposits. All of this information led to an understanding of the original Storega slide. It had initiated about 150 kilometers downstream or downslope of the current scarp, and then worked its way backward through a series of retrogressive slides, as landslides often occur. It stopped when it reached the overconsolidated material, the material that had been compressed by the weight of the glaciers and was denser and stronger. So this kind of combined geologic engineering model of the original Storega slide was very helpful in investigating the current stability by means of static and dynamic slope stability analyses, runout analyses, tsunami analyses based on potential landslides that could have generated them. All this was done within a risk-based framework and came to the conclusions that none of the project-related activities were capable of causing such large landslides. And a really big one was impossible, largely because there was nothing left to slide. All the soft stuff had been taken away by the Storega slide. There was a very small possibility of a smaller major slide with the expectation that such an events would occur with a frequency of about 4 times 10 to the minus 8th per year. In other words, one on average every 25 million years. For the medium slides, the risks were also very low, for a little bit higher for natural slides, and none of the project-related activities would be capable of causing something that big. And even the small ones, return periods of about 100,000 years there. And so the Storega, or the Ormanlaga field was developed. It began pumping gas in about 2007 or so, and has continued since that time and provided a source of energy without any, at least geohazard-related difficulties. So it was, to me, very interesting to work with this group of, this interdisciplinary group of people to see the state-of-the-art tools that they all had to use, the technologies that they used to address this problem that had many, many moving parts. Very interesting to work with them and learn about their disciplines and to see how people address problems in those disciplines. It was very different than things that I would do, for example, in many cases. The emphasis there was on getting it right. Both the government and the consortium of oil companies had risks and rewards associated with developing this field. And they put no pressure on us to sway things one way or the other. They really wanted to know what was the actual hazard that they were facing there. I also learned in that there were a number of trips to Norway for meetings. And I learned, don't eat lutefisk. If you have to be polite, make sure there's a lot of beer on the table. It's the only way to get that stuff down. So next I'll move to the fast category. And this is a landslide that occurred just a few years ago in Brumadinho, which is in the eastern part of Brazil, north of Rio de Janeiro in Minas Gerais state. It's closest to the large town, city that it's closest to is Belo Horizonte, but it's closer to the town of Brumadinho, a small, relatively small town to the southwest. In satellite view, it looks like this. Where we're interested in is the Correio de Feijão mine. The mine is a large iron mine. It's owned by a company called Vale. That's a big mining concern. Within this area, this is about 3.5 miles wide or so, the mine. Dam number 1 is of interest. In this mine, as in many mines, the process involves excavating rock, crushing that rock into gravel, sand, silt, and clay-sized particles, and then processing it to extract a target mineral. The target mineral was iron in this case, but there's a lot of waste material that's left over, the gravel, sand, silt, and clay that doesn't have much ore in it. And that has to be disposed of, and that disposal usually takes place by moving it into a storage facility. And so this waste material we refer to as tailings. And tailings are typically transported to tailings storage facilities hydraulically. They're mixed with a bunch of water and pumped or sluiced to the desired location and deposited there. It's a very cheap and efficient way to move large quantities of soil. It's what was used in the Denny regrade here in Seattle. They're used to fill in the old tide flats where now our stadiums are existing. And so this tailings is pumped through a tailings discharge pipe, and then it's released through spigots, and this material flows down the slope. The water and the soil. The large particles that are heavier settle out first and form what's referred to as a beach behind a tailings dam, and then the finer particles go out into a settling pond where they eventually will settle out of suspension. The tailings, in both cases, the coarse-grained and the fine-grained particles, are deposited by settling down slowly through water, so they're in a very loose structure. And so the great efficiency of this procedure with respect to the cost of moving large quantities of material is also very efficient for creating liquefiable soil deposits. So here's an example of the tailings being ejected and a beach being formed. Here's another one. You can see the beach here in the foreground, but you can see in the background that there is no beach. It's really important in operating these tailings dams to control the rate at which the tailings are being placed. And if they're placed too quickly, you lose the beach, and that means that you're going to have fine-grained soils mixed in with the coarse-grained soils. And those fine-grained soils are going to impede drainage. They're going to weaken that beach area, and the design of these things relies on basically a granular beach, a free-draining beach, to have the strength to maintain stability. So there's different ways in which tailings dams can be constructed. A historically common procedure is referred to as the upstream method. In this method, you start with a small tailings dam, a small starter dam down at the bottom. You fill up the area behind it with tailings, and then you build another dam, a small dam, on top of the last dam. So part of that dam is supported by the previous dam. Part of it is founded on tailings themselves. And you keep building this up until you get to the top. You want to have a nice beach here of granular material, nice gravels and sands that will drain freely and have good strength. And all the fine-grained material that's often referred to as the slimes are retained behind that. It has advantages that you don't need much fill. You have a high storage capacity, but these dams have been notoriously unstable over the years. An alternative and preferred procedure, at least from a stability standpoint, is to build them by the downstream method, where you start with a starter dam and then you raise it, but you raise it by working your way downstream. You end up using a lot more fill, you have somewhat less storage capacity, but it's much, much more stable when you do it this way. The Dam 1 at Brumadinho was constructed using upstream method. And so they built a starter dam in 1976, filled it up, and then continued raising it in a series of raises after that. There were stability concerns after the third raise, and so for the fourth raise, the designer specified that it be set back to try to flatten out the overall slope a bit. And so the rest of the raises were constructed that way. Some of the embankments had low permeabilities, which is not desirable because it impedes drainage of water from the tailings. There were a couple with drains, but there was no internal drainage, which also would have been highly desirable. The 10th raise and final raise was constructed in 2013. The last fill was placed in 2016, and we ended up with an 86-meter thick pile of tailings here. The dam had a crest length of 720 meters, and it looked like this a few years after construction. There's a former pond area, which has by that time been overgrown with grasses and shrubs. There were surface drainage channels to deal with surface water and keep them from getting into the tailings. There were also surface water interceptor drains to keep water from coming off the hillsides and into the tailings. The setback area is shown here. There was a water dam that retained water for the processing plant that was off to the side. Is referred to as Water Dam 6. Looking at it from a different view now, you can see the Dam 1 here and Water Dam 6 over here. The processing plant was located about here. There was a stockpile area and a cafeteria or canteen and some administrative office buildings for the mine located down here. There was also a video camera set up called Camera 1 on the hillside above the processing plant, and another one back behind the dam looking out over the former pond area. If we look at the records of construction, they're notable for the fact that these raises were designed by 5 different designers and constructed by 11 different construction companies. So very inconsistent in the designs, the analyses that were done to support the designs, the kind of the philosophy of how these things were being built. It's not the best approach to take in a situation like this. They did perform stability analyses for each of the raises. The possibility of liquefaction was not considered, despite the fact that they had very loose saturated materials, granular materials. This is not a seismically active area, and the engineers there believed that liquefaction would only be caused by earthquakes. My PhD research was on static liquefaction. I ended up doing a lot of earthquake stuff, but it wasn't part of my PhD work. Liquefaction does not require earthquakes in order to occur. Each of these stability evaluations was reviewed and approved by a safety auditor, an independent firm that was engaged to do that. The stability was generally evaluated using drain strengths, assuming that the tailings had been developed slowly and that pore pressures were very low. They did some analyses using undrained strengths, but peak undrained strengths, which are considerably higher than the strength that a liquefied soil would have. There were concerns about high water levels within the tailings, and so in early 2018, they began installing deep horizontal drains from the face of the dam back into the tailings to attempt to draw down the water level within the tailings. If the water level would come down, the effective stresses would increase and the dam would become more stable. In December of 2018, they began installing some vertical borings in order to install instrumentation, piezometers to measure pore pressures, inclinometers to try to measure deformations. They got 9 of them in by January 20th of 2019. On January 21st, they began the 10th boring, and 4 days later had reached a depth of about 66 meters. On January 25th, they were out continuing to advance that boring. This photograph is a still that was taken from the video camera of Camera 1, looking at the face of the dam at about 12:30 in the afternoon, lunchtime. You can see the drill rig out here. If we zoom in, you can see it better. There was other equipment and personnel on the face of the dam at that time. I was in Christchurch, New Zealand at University of Canterbury, where I was teaching a class that winter quarter. And someone came into my office and said, there's a video you got to see. And so I went to his office to look at it, and it was a video from Camera 1. And what you'll see here is the face of the dam at that time, and the dam will, I did hit the button, will fail right in front of your eyes. We're seeing static liquefaction here. You see the front part bulged out, the back dropped down, continues to drop down, and you're seeing a 100-foot wall of mud, very heavy mud because this was iron-rich material. Came down, filled up the little valley, it came up and destroyed all of the trees, destroyed part of the processing plant, and then started sliding off to the right in this picture. Kicked up a lot of dust. If you look in the lower right, you can see the material is moving. It moved 20 miles an hour at one point. So 1 minute after initiation, the view is obscured by dust, even 2 minutes after, but as the dust started to clear, 3, 4, 5, and 10 minutes after, you could see the level of devastation that had occurred at Brumadinho, at this mine. Almost 10 million cubic meters of material were involved in this failure. They came down and damaged the processing plant, they damaged Water Dam 6, and they buried the stockpile area. Camera 2 was also running. This still was taken just before the initiation of the failure. You can see raise number 10 here at the far edge, the face of the dam. You can see some of the old spigots that still remain. 10 seconds after triggering, a chunk of raise number 10 is gone. So the initial slide was shallow. It took out the 10th raise and a shallow, relatively thin zone behind the face of the dam. But as the failure progressed, you can see that more and more of the tailings disappears. So there's a retrogressive failure mechanism here. And 40 seconds, 50, 60, 70, and 100 seconds when the video that I had at least ended. And you can see that essentially all of the tailings has flowed out, has been removed. So looking downstream, you can see where the canteen was. The canteen and administrative offices were buried. There were 250 people in there that never knew what hit them. They were all killed. 20 more people died further downstream. The flowing materials eventually, 5 miles later, entered and contaminated the Paraíba River, which had provided, before that time, a third of the drinking water for Belo Horizonte. Looking back upstream, you can see the fluid nature of the material. Down in the lower left was a railroad bridge that was taken out by that flowing material. So several investigations began almost immediately. There was an expert panel that was convened by Vale, the company that owned the mine. Peter Robertson, who many of you know or know of, was the chair of that panel. The government also formed what they called an extraordinary independent committee to investigate the dam. It was a blue ribbon panel that was chaired by a former Chief Justice of the Brazilian Supreme Court. And they established an investigation team that had Brazilian and US law firms that specialized in internal investigations. There's another word for corruption. Ernst & Young looked at the business aspects of how Vale had done things. There were 2 Brazilian geotechnical firms, and they hired 2 consultants that were called the USA consultants, Ed Idris and myself, to provide some expert advice and review. So the committee's scope included not just the technical aspects of this, but also looking at corporate governance and culture, compensation policy, communications within the company, and their relationships with these external dam safety auditing companies. And there were also a lot of litigation-related investigative efforts. Technical conclusions were that the fragile nature of this dam and the need to mitigate its risk was known to Vale for a long time. Low factors of safety had been reported many times. Inadequate drainage had been reported many times, and high water levels in the tailings had been reported many times. Nothing was done about it. The designers and the safety auditors kept on signing these stability declarations. Scott Olson of University of Illinois was engaged to advise them based on his interpretation of the strength data. That computed factors of safety of a little over 1.06. But the company that retained him reported a factor of safety of 1.3 using higher strengths that were not justifiable by any means that Professor Idris and I were aware of. A German firm called TÜV Süd was engaged. They computed a factor of safety of 1.09, and they said it was okay based on a criteria of a minimum allowable factor of safety of 1.05. How many geotechs in this room would like to have a slope with a 1.05 factor of safety? It's ridiculous. There's no way. It's later found that TÜV Süd was pressured by Vale into signing that with a carrot being held out of future contracts. There were political aspects to all this as well. The government of the state of Minas Gerais created a body that would streamline approvals of mining applications. So the approvals went from 3 stages down to 1. They took from years down to months, and they increased the number of licenses tremendously. The failure was due to static liquefaction of these tailings materials. Here's a stress strain curve of this material. It exhibits a peak strength at low strains, and then the soil skeleton just collapses, and it's able to mobilize almost no strength after it has liquefied, which is consistent with the fluid nature of those materials that we saw in the video. It was triggered by slow, sustained creep of tailings. I used to see this in the lab when I was doing my PhD work all the time. Creep of granular materials is generally not recognized, or at least underappreciated. This was complemented by a loss of capillarity-induced strength by saturation with surface water that had gotten into the embankment. The drilling of the vertical well was postulated as another potential cause because it was occurring right at the place and the time where the failure occurred. It can't be ruled out, but it seemed to us to be very unlikely. In the aftermath, 16 people have been charged with murder, charged with homicide for this, including the CEO of Vale. Vale's market capitalization dropped by 20%. It's recovered since then. They've been ordered to pay a fine equivalent to $7 billion for social and environmental damage. Our Securities Exchange Commission just 3 weeks ago sued Vale for raising money from investors fraudulently. More than 20 other Vale tailings dams are considered to be dangerous, and residents below 10 of them have been evacuated from their homes now. It's not just Brazil, and it's not just Vale. In the big picture, this shows the number of tailings dams in all of these countries. And Steve, Australia's in first place. Canada is second, but in those countries, tailings engineering is practiced at a very high level. Brazil is in third place, and South Africa and the US round out the top 5. If we restrict ourselves to these upstream tailings dams that have high risks associated with them, South Africa is by far the leader, and the US is in second place. So this is really a global problem. Static liquefaction is an important, pervasive issue in the tailings business. These materials can creep, and so if it's stable, it doesn't mean it's going to stay stable necessarily. It needs to be looked into. More research is needed. There are groups that are forming to try to advance tailings engineering practice. Mining is a big business. I think everybody realizes that. Tailings, disposal of tailings is a significant cost to them. And some companies put safety, long-term safety, in the back seat compared to short-term profits. That's what happened in this case. Corporate governance and communication plays a huge role in the safety of these types of facilities. Bad news needs to be given, it needs to be heard, and it needs to be acted upon. That did not happen in Brumadinho. Engineers need to be involved in corporate governance and have the ability to communicate with decision makers. That didn't happen in Brumadinho. There are a lot of tailings dams that have substandard designs, substandard construction, and they're dangerous. So it really is a worldwide problem. So finally we get to the slow case. Another relatively recent one. This is the Millennium Tower, a high-rise structure in San Francisco. It's in the south of Market area, bounded by Mission Street on the north, at least Project North, and between Fremont and Beale Streets. It's a luxury high-rise tower, 58 stories. Joe Montana lived there, which if you're from San Francisco, it would make everybody want to move there. You can buy a one-bedroom condo for only $3.8 million. And this one looks out at other buildings. Some of the others, if you have more change in your pocket, you could buy the penthouse for $13 million, which sounds like a lot of money, but you have to realize it's got a balcony. It's right across Fremont Street from the Salesforce Tower, and Salesforce now kind of dominates the San Francisco skyline. The poor Transamerica Pyramid is kind of an afterthought now. It's a massive building, and it's right across the street from the Millennium Tower, which is quite a bit shorter. The Millennium Tower complex actually consists of 3 structures, a high-rise that's 58 stories tall, There's a low-rise structure, a mid-rise structure that's 12 stories tall, and they're connected by a low-rise structure. The high-rise is the one we're interested in. It's supported on piles that we'll talk more about later. The subsurface conditions here consist of, underneath the structure, 15 feet or so of young bay mud, a very soft, compressible, normally consolidated material. It's weak. You wouldn't build anything of any consequence directly on San Francisco Bay mud. Below that is a marine sand that's about 30 feet thick, a uniform sand, clay, some clay in it, medium dense to dense. Below that is the Colma sand, which is a very dense, silty fine sand. It has some clay. The clay is hard within it. It's been used as a bearing layer for years in San Francisco foundation design. Below that's the Old Bay mud, or the Old Bay clay. That's a highly plastic, over-consolidated, stiff to hard. Over-consolidation ratio averages about 2 in the upper portion and about 1.7 below that. And bedrock is about 200 feet deep here. So the tower was originally going to be a steel frame structure, but it was changed to a concrete structure because steel prices were fluctuating rapidly and fluctuating up more than they were fluctuating down, so concrete turned out to be cheaper, and the developers chose to change it. Originally, parking was going to be below the high-rise tower, and there's a benefit to putting parking below a high-rise because you're going to excavate out a lot of soil and compensate for a lot of the weight of the building that you're going to build. And they decided to move that parking to be under the low-rise and mid-rise sections so that they could get the high-rise tower built sooner and proposedly sell the condos faster and start getting revenue coming in from this project. So the consequences of these changes were that the building turned out to be a lot heavier than was originally planned, and the load compensation benefit due to removing soil from below the high-rise section was effectively eliminated. So the stresses that were imposed on the soils below the foundations were much, much greater than they would have been if the original plan had been carried through. There are other high-rise buildings in this area of San Francisco. Millennium Tower is in the middle. It's building number 1. This table shows these buildings and their foundation systems. The ones that are in orange are founded on piles that end in the Colma sand. That was a very common way of building high-rise buildings in those locations. The Millennium Tower is far and away the tallest of those buildings, however. The ones in blue are on mat foundations, no piles at all, but they all have relatively deep parking garages beneath them. And so the net stress imposed on those soils, the weight of those smaller buildings minus the weight of the soil that was excavated, is not so great. They can get away with mats there. And then there are 3 buildings, including the Salesforce Tower, that are supported on piers that go all the way down to bedrock. So the situation kind of schematically for the Millennium Tower high-rise looked like this. There were 950 14-inch precast concrete piles driven into the dense Colma sand layer. They were connected by a 10-foot thick, heavily reinforced mat. They required an excavation, so they had to dewater the excavation. That meant pumping out water, drawing the groundwater level down around that excavation. When you lower the water table, the effective stresses in the soils increase and consolidation occurs, so more settlement occurs. They ended up with effectively a forest of piles down there, and here's this photos taken shortly before the mat was poured. So the stresses now, the weight of the building, are being transmitted by these pile foundations down to the Colma sand. And it's going to impose stresses on that Colma sand, but more importantly on that Old Bay clay, this over-consolidated clay. Usually materials that are considered to be heavily over-consolidated don't consolidate very much, but these were heavy loads. And so settlement calculations needed to be performed, and they were performed by the designing geotechnical firm. These were based on their subsurface investigation, based on laboratory tests that they performed and that other people had performed for surrounding projects previously. They predicted ultimate settlements on the order of about 4 to 6 inches or so. And they monitored settlement as the building was being constructed. And by the time it was completed, and certificate of temporary occupancy issued, they had more than 8 inches of settlement before anybody could even move in. But they continued to sell the condos, and settlement continued. They started suffering damage, cracks in the basement walls, water getting into the garage, differential settlement between the high-rise and the low-rise section. Eventually, they needed a ramp in the lobby for residents that use wheelchairs. There was damage on the outside of the sidewalks and the cladding. So this settlement continued to occur. It became known to the city in about 2008. There's evidence of a lot of emails going back and forth between the city and the designers and the contractors. That settlement was accompanied by some tilting. The top of the building moved about 6 inches to the north and 14 inches to the west. The tilts corresponded to relatively small angles, but they were noticeable. If you went into one of the condos and put a marble on the floor, the marble would roll. The marbles would probably roll in my house, but this was due to this tilting. The general public became aware of this in 2016 when 60 Minutes decided to do an episode devoted to the Millennium Tower. And so when 60 Minutes comes to town, you know you've got trouble, I guess. And their story led to other stories. And if you are the designer or the builder or a resident of this structure, you don't like to see this sort of thing. It became notorious. There was a stigma attached to the Millennium Tower, and property values plummeted. And a lot of the residents here were older people who had retired and put their savings into their equity into condos here. They wanted to live downtown San Francisco and walk to everything and have all the cultural benefits. And this was really a traumatic thing for them. So, as you can imagine, again, particularly now that we're in the US, litigation ensued. The main parties were the Homeowners Association within the tower, the developer, the Trans-Bay Joint Powers Authority, which was developing the Trans-Bay Transit Center adjacent to the Millennium Tower, was also named in these suits. Salesforce was named, and this building just to the north, 350 Mission, was also named in some of these lawsuits. There were many subcontractors involved, as you can imagine. There were many insurance companies involved. There were many, many attorneys. The first email I got after getting involved with this was CC'd to over 200 attorneys. I counted them. There were a lot of experts. All the attorneys started hiring experts. I knew almost all of them. And they all had affiliations with the various parties. And basically everybody sued everybody. So it was a mess as far as I could see. But while all this was going on, the building was still settling and it was still tilting. And so there was going to, originally, the lawsuits would normally be handled in court, but a trial would have been extraordinarily complex. It would have taken several years for the trial even to occur, and the appeals would have taken another 15 to 20 years. And nobody really had the stomach for that, particularly the retirees who had bought into the Millennium Tower. Didn't have 15 to 20 years to wait for this sort of thing to happen. And so there's a mediation team that was headed by Dan Weinstein. There were 2 retired judges and 3 very experienced attorneys that had expertise in various aspects of this case. And they were going along trying to understand geotechnical engineering and listening to all the experts, and they finally threw up their hands and said, we need some help. And so I was asked to become what's called a neutral expert on this case. And so my job was to be neutral, to advise them on the technical aspects of the case and kind of translate engineering talk to English, to provide an unbiased basis for allocation of the responsibility for the losses that had been incurred here. So I had to decide who was going to pay how much on the basis of at least the technical considerations, which were not all of the considerations at play here. And then I provided input to selection of the fix that was going to take place here to try to stop the settlement and recover some of the tilt that occurred. These other parties, the Transbay Transit Center was a really cool structure, but as far as this case was concerned, it was a hole in the ground. It was a 1,400-foot long, 85-foot wide, 65-foot deep hole in the ground that shared a property line with the Millennium Tower. It's a big excavation. They had to do dewatering, and they used a slurry wall to try to prevent the effects of their dewatering from going out beyond their property, and they had mixed success with that. Here's the excavation, the bracing. It was a big project in and of itself. Salesforce had excavations for both the tower and the podium structure adjacent to it. Here's the tower excavation. Here's the podium excavation. The Millennium Tower is on the left here. The Salesforce Tower is on the right. It's just across the street from the Millennium Tower. And so these wells, these dewatering activities had the potential to draw down water levels and potentially influence the settlement and tilt of the Millennium Tower. The 350 Mission Building was a shorter building just to the north. It only had a 32-foot deep excavation. They did some dewatering, but this was not considered to be a major player in this particular case. The different parties had their positions. The Homeowners Association said the original design was deficient, the construction was defective, they were dewatering for too long. The Transit Center contributed to the settlement and tilt with its construction activities, and the Salesforce Tower did the same thing. The developer said that the settlement and tilt was stabilizing. It was going to be okay, but it accelerated after the adjacent construction began, and they blamed the Transit Center, Salesforce, and 350 Mission for contributing to the additional settlement and tilt. The TJPA, which was essentially the Transit Center, said that the original settlement calculations were flawed, that the Millennium Tower had already settled and tilted excessively before the Transit Center construction even began. And they had instrumentation records and pumping records to refute the arguments that that their excavation bracing had moved or their dewatering had caused problems for the Millennium Tower. And Salesforce had essentially the same position as the TGAPA did. So this mediation process involved many, many meetings between the mediation team and the lawyers and their experts. Some of these meetings took place with everybody in attendance. Some of them the mediation team met with individual parties, and we would be in a law firm and go from conference room to conference room to talk to these different parties. Really a fascinating thing to be participating in. They all had, as you can imagine, different interpretations of the data and the case, and they all had their justifications for their data. My approach when I was brought into this was to try to meet with all of the experts. And so after listening to all this stuff, I told the mediation team that I wanted to meet with all of the experts, and I wanted to meet with them with no lawyers in the room. And to their credit, they backed me up on this and fought to have this meeting take place, and it did take place. All the attorneys, the other attorneys, were quite reluctant to have their experts off the leash and out from under their control. But we had this meeting, and before the meeting, I gave everybody a homework assignment and said, I want you to tell me what you would predict the settlement would be 50 years from now, based on all of your assumptions and calculations. If nothing was done, how much more settlement will occur? How much more tilt will occur? And so they sent me all of their estimates, and I compiled them all the night before our meeting, and I presented them to them. And they showed settlements ranging from about 2 inches to 29 inches. And so this is why I didn't want the lawyers in the room. So I said, all right, come on, people, we can do better than this. And I gave them 2 weeks to either confirm or revise their calculations. So they went back and did that. We got together in San Francisco 2 weeks later, and they were on the order of 6 to 8 inches or so. And so we established then a non-advocacy based or influenced maybe idea of what was going on and what was likely to go on, and of the properties that should be used in these kinds of analyses. the mediation team that I worked with was just a dream to work with. I mean, these guys were fantastic. I really enjoyed it, professionally and personally. And they backed me up anytime I wanted to do something. They backed me up. You know, lawyers get to make demands. I mean, that's an official term. So I got to make some demands myself, and I never get to make demands. I never demanded anything of Laura or her predecessors. I don't get to demand anything at home, but I got to make some demands here, and it was liberating. It was great. So I listened to all these presentations. I studied the data. I did some of my own analyses, met with all these parties, with the mediation team, considered all of their positions and their justifications, and I came up with my judgments on how the responsibility should be allocated between these different parties, what fraction of the damages each of them should be responsible for. But that was just based on technical grounds. At that point, I bowed out and let the attorneys battle it out over the remaining issues, which were substantial. Things like contracts and insurance. Man, I learned more about insurance and insurance towers than I had ever thought existed. Fraud, there were all kinds of things at play here. But I was out of it after that period of time. About a year or so, maybe a little more than a year later, a settlement was eventually reached, a global settlement, over $500 million in damages that got distributed through that process. So my observations here was that being a neutral expert is great. I loved it. It was the most interesting thing I've ever been involved with. It was very challenging, and there's a lot of pressure involved. A lot of pressure, because there were big bucks, and there were attorneys who were aggressive, and they questioned me, and I had to respond to them. You have to know what you're talking about. You have to be patient. You have to have a good poker face, which comes naturally to me. I only have one expression, so that's what 40 years of studying dirt will do to you. The technical experts were the cheapest people in the room. We were also the worst dressed people in the room, probably because we were the cheapest people in the room. These mediators were sharp people. They picked up the technical stuff very, very quickly. The mediators had to deal with a lot of stuff, not just these kind of technical issues that I was involved with, but the legalities, the economics, the insurance, psychological issues. Watching Dan Weinstein operate here with all the different teams was really a fascinating process. It was like watching a maestro conducting an orchestra. The legal aspects, to me, were very, very interesting, and being on the inside and getting to, even just when we had our lunch breaks, to talk about, try to figure out what the different parties' strategies were, was very, very interesting. And they let me be part of those discussions, which I really appreciated. Attorneys represent their clients. You have to recognize that if you're involved with something like this. And they do it forcefully, vigorously, and aggressively. It's a big deal to them. Experts serve as advocates for their parties, and their interpretations of technical data can be quite different, and it can be challenging to try to get people, even dealing with what you think would be factual information, to kind of converge on something that is more appropriate. So some of these interpretations are more reasonable than others. You really need to dig deep to evaluate how each of them can be justified. So to summarize, I hope I haven't gone on too long. Geohazards are important. They affect physical and economical well-being of people and their communities. They're also interesting. They involve interactions with soil, rock, and water and structures. Those are all technical aspects that are interesting, but when you get involved with larger projects like this, you start to see how the interactions with people become more important. It's something you don't often see in a research type environment. These kinds of projects and my work here for 36 years at the UW allowed me to go to places I never would have imagined going to and doing things I could never dreamed of doing. I enjoyed my teaching here. I enjoyed the research. I enjoyed my service activity, most of it. Enjoyed my colleagues in the geotechnical group very much. Enjoyed my students. Enjoyed the big, interesting, difficult, real-world projects that I've been able to work on. And I'm enjoying my retirement, especially getting to spend it with the person who's helped me make all of this stuff possible. and supported me over all these years. So thank you very much for your attention.
You enjoy working with your colleagues beyond just geotechnical engineering, though, right?
Oh, yeah, yeah.
We've certainly got time for some questions, but I'm going to ask you if you have a question to use the microphones that are on either side of the room. Question? Okay. I have a question. I can use this microphone.
Okay.
So I actually come from a mining background. My dad started out as a mining geologist, and I have other geologists in my family who've worked on tailings dams. Is there it seemed like they were monitoring in the failure that you showed us, but are there strict requirements on how those get monitored? And is the concern that people are not taking that data and using it or interpreting it appropriately? I guess how much does that help reduce the risk?
It's a very good question, and a lot of people are very interested in trying to monitor these things. What makes it very tricky, really tricky, is that when you get close to having a static liquefaction triggered, when the stresses get to a certain level, only a tiny increase in stress when applied rapidly is required to trigger that liquefaction. I did it accidentally in the lab many times during my PhD work, because back in those days, in the old days, I would walk through the snow uphill to get to my lab, and I'd have to twist a dial to apply load. And if I twisted it a little bit, if I twitched a little bit, I would kill my sample. And now, I would have a computer to do that for me. But the strains that are at which those failures are triggered are so small that you really have an extraordinarily difficult time detecting any movement that would foresee a failure or precede a failure like this. So they actually had, with all of these projects, I've just given a very brief overview. They had radar systems, they had all kinds of systems trained on the face of that Brumadinho Dam. And we looked at all of those records, and you could not see anything that would have shown you that failure was about to occur. So it's a really tough thing to be able to do. They had pore pressure transducers, they had inclinometers where they would read these things, at least periodically. Eventually they got them hooked up to a data acquisition system where they could monitor them continuously, and there was nothing that foretold that particular failure. It's the nature of the materials that makes monitoring for this kind of event very difficult. Joe?
Steve, I have a couple of questions about the last case history, the Millennium Tower. So I don't know to what degree you can answer these questions. But the first is that you noted the settlement, the legal settlement in the case. To what degree did that reflect the decision of that mediating group? Were they the individuals who ultimately determined what that settlement was going to be, or is that something that the various parties had to agree to?
Everybody has to agree to it. It's a negotiation process. So mediation differs from arbitration. In arbitration, there's an arbitrator that has the say, and they can make those kinds of decisions. But mediation is a negotiated agreement between all of the parties, and there were a lot of parties, and nobody ends up getting everything they want. Nobody's happy, but they all end up at least satisfied that they've gotten what they can out of that situation.
Since we're recording, can you paraphrase his questions?
Sure. That particular question had to do with whether the mediators were the ones who were making the decision on these allocations, or whether it was a negotiated settlement. And my answer, obviously, was that it was negotiated.
Okay.
And the related question is that how did that distribution of responsibility wind up? Is that a matter of public record as to, the question about the dewatering versus the inadequate foundation? Is that an out?
It's not made public.
Okay.
I can't make my recommendations public. I'm talked around a lot of things here to just be able to talk about the case. And I don't know what the final numbers were. I wasn't told how they were distributed. You know, my allocations were a starting point, and then they took off from there. So I don't know how it ended up.
And my last one, and I'll make this really quick, is that when I look at the litigation that followed OSO, it kind of reminds me of Millennium Tower and, you know, very complex undertaking, but there was extraordinary technical insight that was contributed to those cases. And I always feel that it's kind of lost because it stays behind the veil. Does that ever become part of the public record, or any of this kind of really interesting technical work that's done to support the cases?
Yeah, it depends to a large degree on the attorneys and the various parties and what they're willing to release. I know that John Stewart has written a paper. He was one of the experts, and he was allowed to by his party, and it's in review with ASCE now, and that will have a lot more information than I felt comfortable talking about here, and that I should have talked about. So I would look for that paper. Other parties, I think, will tell their experts, nope, you can't talk about it. But you're right, in a lot of cases, a lot of information never comes to light that would ideally be available to us all to learn from.
It was a great talk, thank you. But I want to go back to the Millennium Tower. So there was settlements, but then is life back to normal? So what are the risks now into the future in that area? And what
Well, there's the story continues. There is a fix that is being undertaken to stop the settlement with a series of pile foundations that are going down all the way down to bedrock, that are being built around the north and west sides only of the structure. And that process has not gone smoothly. When they started installing these piles, they were getting more settlement occurring just due to the installation process. And I don't know any of the details. There may be some people in here who are involved with this that would know those details. And I've been told by the mediation team that I should not even ask people about it. So all I know is what I read in the newspapers, but I do read the newspapers when I see stories about this. And so the plan was to put these piles in around two corners, the corner that had been settling the most, to connect those to the mat foundation. And that's a tricky thing because under seismic conditions now you're going to have piles that are very stiff because they're going down to bedrock. If you just connect those directly to the mat under earthquake loading conditions, you've got very stiff resistance in one direction and not in the other direction. The mat wasn't designed to take the forces that are going to come into it from that very stiff support. And so they had to design kind of a fuse that would be stiff and strong under static conditions, but that would yield and dissipate energy under seismic conditions when that structure would start rocking during an earthquake.
Most of us go to the AGU meeting there, so it's probably a good idea to avoid the area.
Yes.
We have another question over here first.
Steve, getting back, excuse me, there's somebody else talking?
I believe so, yes. Is that not working?
It's working, or, oh yeah, it is working. That was a really wonderful talk, Steve. I enjoyed it greatly. In thinking about the Millennium Tower, and actually a theme going through this and the Brazilian tailings dam failure, maybe more of a philosophical and ethical question. For lawyers, it's pretty clear who they work for. And they can put out for anything that has even an iota of plausibility to it. But engineers, who do engineers really answer to? Do they answer to their clients and what their clients want to have done? Do they answer to the regulatory framework in which they work? Do they answer to the standard of care that we all depend on as a profession? Do they answer to ultimately the science that underlies what we do? That's kind of a big question, but in looking at this, who are the engineers answering to? And when their clients ask them to put out an analysis that's favorable to the client, what do?
I don't know. It is complex. It's complicated in this country, and in other countries, the standards of business and of engineering and other professions are different than they are here, and it's hard to understand them in some cases, as in the case in Brazil. They're just so different than the way we do things here. I'm sure that ASCE's ethics group has canons that tell us how we should behave in situations like this. I probably should, like everybody else, go back and read up on them again. I think it ends up being kind of a personal decision. I think all of the people, all of the experts that I worked with believed their interpretation to be correct, or at least highly plausible. And I couldn't see anybody that was doing something that I thought was I'm going to say underhanded, but beyond the bounds of what would be considered reasonable. But if you're on the edge of reasonability and several different things, those assumptions can compound into something that in the end does not seem so reasonable. So my job was to try to sift through all of that stuff, which I did respectfully and as accurately and thoroughly as I could to come up with the allocations that I ended up presenting. But you're right, it's a complex issue on many levels.
Yeah.
Bob.
Is this okay now?
Yeah.
Steve, the figure that you showed with the numbers of tailings dams in different countries was very interesting. Mm-hmm. Is there any data that you could show us, or anybody else, where you could plot below that the number of failures and then also a time scale? Because I get the feeling that dams that were built 40, 50, 100 years ago were, especially the upstream construction, they're really terrible. But how many of those actually fail? And then how does time and what the profession has learned about those things must improve practice, in especially Australia and Canada?
Yeah, I think practice has improved in many areas. The tailings dams have been outlawed, for example, in Peru and Chile. Upstream tailings dams have been outlawed, and there's a move now to dewater the tailings before they're deposited, so that this kind of hydraulic mechanisms are not being used anymore, particularly in the upstream dams. But there's still a lot of them out there, and so even though there aren't many new ones being built that way, there's a big inventory of them out there. There are lists of tailings dams failures. It's not clear that it's a very complete list, because a lot of them fail and we never know about it. It's just not publicized in any way, and it for obvious reasons. Yes.
Hi, Professor. Thanks a lot for the interesting presentation. And I'm a PhD student of our department, and I have a little bit general question for you. That is, recently I found that the civil engineering research, they are more interdisciplinary towards, like your moderation experience is very interesting. Like you need to moderate different kinds of opinions from different kinds of peoples. So I'm very interested about that. Like me, I'm a student in the transportation engineering, and I need to learn a lot from other departments' science, like the AI-based knowledge, like the mathematicals, like the material science. So keep this research and keep me research ongoing. But I feel really not focused on something. So I'm really interested about your moderation experience. So could you please give us, like, I see so many freshmen in this here, and so could you please give us some suggestions about how we can keep concentrate on something, and especially in the civil related research? So that's my question. Thank you.
I'm not sure I heard all of it clearly. Masks are a problem here. I think that it's important to, at least my experience has been that it's important in situations like this to rely on fundamentals. Very often when I'm asked to help out on some particularly complicated problem, I end up seeing that it's really fundamental issues that are involved. And if people thought about things in fundamental terms, they wouldn't have needed to hire me to come in and try to help them. When you have differences of opinion like this, it's difficult. It requires a lot of patience and understanding to try to see the points of view of the different people. I think that it requires good communication skills. Not to say that I necessarily have them, but the more you can, as a student, improve your exposure to non-technical subjects and improve your writing ability, improve your speaking ability, communicate with people outside of your own area, you benefit from that because those are the people you'll be dealing with later in your career. I hope that touched on part of your question at least.
Thank you. Yeah.
Thank you for the talk, Professor. Are there any lessons from these failures you've documented, I'm especially thinking San Francisco, that could be translated into prevention locally? We're fine.
I think, in the case in San Francisco, it could have been avoided by the original designer. When the building became much heavier and when the foundation conditions changed with respect to the garage, and I don't know that any of the details of their contractual relationship between the original designer and the developer, but it would seem to me that would have been time for a reset to occur and for a much more detailed exploration program to take place. There's often a tendency, I think, in all of our design activities and maybe even more so in geotechnical engineering to rely on precedent. What worked here will work there. And you can kind of fall into a trap of critiquing different things because we didn't do it before. But you can fall in kind of the inverse trap of not trying different things because they haven't been done before. And the standard in that part of San Francisco was to support buildings on piles in the Colma sand. But that obviously didn't work in this case. If they had had more detailed information about the subsurface conditions, say more test data, more samples, they likely would have seen that the conditions were not what they had assumed them to be and would have predicted settlements high enough that they wouldn't have built it that way. They would have said, you got to go to bedrock. And that would have added substantially to the cost of the structure. Their piles were 80 feet long. They would have had to be, they would have had to go into the bedrock there, which was not very good bedrock, this Franciscan formation there. It would have been 220 feet long, almost triple the length, and with the attendant difficulties in driving. And so I think every project has to be recognized as being unique. Every site has to be recognized as being unique. Precedent helps, but you can't over-rely on it.
Thank you.
Yep.
I think we have one more question in the back. And Steve, I think I'll ask, there's one in the back. I'll ask you if it's okay to follow up with Steve afterwards. Is there one more in the back? Please go ahead.
On a scale of 1 to 10, how would you rate the quality of your engineering design 40 years ago on the Kramer Dam?
The quality of what? Sorry.
The quality of engineering design you did on the Kramer Dam 40 years ago.
Well, I would have, these days, I would have gotten Plaxis or Flak and built a nice refined mesh of my 8-inch dam, and it would have been, maybe I could have made it 7 inches or something and saved the client a lot of money. But hasn't failed as far as I know. Someday I should go back and see if there are any traces of it left. Thanks for the question, though.
Steve, why don't you close us out?
Thank you for a masterclass in what the totality of engineering can be and should be. And Steve, thank you for being an excellent colleague over the years.
Thank you, Steve.
Yes, thank you very much. Very interesting. Thank you for being a wonderful colleague for many, many years.